Hi friends, in this video we'll just discuss about how when a vapor is entered into a chamber, how it is being get occupied and what is the distribution, and and the air which is already present inside the chamber, how it has been thrown away or thrown out of the chamber. So these things we'll just discuss and we'll try to simulate and look over the velocity and pressure counters, and we'll try to postulate the graphs from the given details. Okay, this, so as you see on the screen, so this is the benzene vapor that is been getting into this chamber where air is already present. So this is the chamber, and this section is just air or atmosphere. We can say that this is an atmosphere. So I will give these as an outflow conditions. So outflow means there is no gradient across these diffusion gradient across the walls or along these sections. So if there is no diffusion gradient, it does mean we need not give any pressure outlet or you need not mention anything. There automatically it tries to calculate the values from the interior parts or from the values that are present here, right? So it will just extrapolate the values here. So depending on those conditions, you just try to extrapolate and it will create the boundary condition which is required. So I'll just show you the setup. So this is a simple setup. What you can see on the screen, I have activated Y as 9.81. So my echo from the figure, you can see that it is in the down direction, but actually it is in up direction. So Y is 9.81. That's the reason why I have given 9.81. It is a transient condition. So you need to on the multiphase, right? So go to models. I have activated mixture model and I've activated implicit body force also, the dispersed phase, because it's not a, it doesn't have a sharp interface. It is a dispersed phase because air as well as benzene vapor will not have any considerable surface tension, so it will try to penetrate into the medium. And you just on the energy, just click on the energy. Then for the models of turbulence, I am activated K epsilon with scalable and realizable as in models. So realizable, why I have activated, because there are so many eddies that would be formed there. So in order to have that turbulence nature captured properly due to the eddies, I have activated K epsilon realizable model. And then you just click on the materials, go to fluid edit, and try to bring the benzene vapor. So you can find the benzene vapor from this. So you can find the benzene vapor, click on benzene vapor, copy, close, then close this. Again go to multiphase and go to phases. So primary phase as air, secondary phase as benzene vapor. The phase interaction, just leave it. Drag coefficient is a normal scalar nomen, slip velocity is minimal, and there is no surface tension coefficient because both are gases. Just click on close and then go to boundary conditions. In the inlet, as I stated, benzene inlet with the pressure inlet, go to edit, and the value is 50,000 Pascal. Click OK, and the temperature also I need to mention, which is 330 Kelvin. Click OK. Next, outflow. Outflow is all those sites. So all these sites, this is 1, 2 and 3 outflows, or 3 sites which are been given with the boundary condition outflow. Give that as outflow and just go to methods. So coupled scheme what I've used, try to initialize, and after initializing, patch the entire surface with temperature 300 Kelvin. Patch it, patch. Then go to phase 2. There is no phase 2 initially present in the entire cabin or outside also. So try to patch it, close. Then try to run the calculation. So with the time step as 1 e power minus 5, number of time steps are given 10,000. Click on calculate. So now you can see on the screen. So here it is from where the benzene vapor is been entering into the chamber, and the remaining air is getting evacuated from the chamber. So I ran through few time steps. So initially I'll just go to 0, apply, close it. I'll just write activate symmetry with that as my variable pressure. So initially everything is at the atmospheric pressure. So with reference atmospheric pressure is 0. It's a gauge value. It's not absolute, right? And here it is 50,000 Pascal. So on next time step itself, you can see how the pressure gets varied. So the entire pressure here is been going down with respect to the values continuously. You can see how it is getting varied. So the entire distribution can just verify. After so these many time steps, it is getting varied in this way. So we can try to have a plot also for this pressure. So we can check it velocity. It just started. So here from the benzene is entering and air is leaving. So that's the reason why both are having a high velocities at that point. And you can see these are the outflows. That's the reason why it's going there. You can see. So there is a formation of eddies here, and the benzene is directed towards the out from the cabin. Direction is also towards that way, right? So it is so obvious. We'll just also check the phase 2, which is benzene, how it is been distributed, how the volume fraction is being distributed with respect to time. So time t equal to 0 of benzene is just been getting entered at time 0.009 seconds. It's bit occupied. So time 0.095 second. It entered very in a great extent into the cabin. So now you can see at 0.127 second it's occupied very much in a good amount. So according to this, the recirculation is happening here, and there are zones where the benzene is least occupied or not occupied, and it is leaving the cabin. So this is so clear that when you're trying to fill anything, so there is a formation of eddies due to the openings, and you need to be cautious about those things before filling. And we can just check the formation of eddies capacity, or quantifying the eddies to what extent it is being occupied. We can just go to the vortex core, select this velocity dot invariant q, which gives the values magnitude of the formation of the eddies indirectly. So here it is huge in value. It is around 8.89 to 10 power 6. Maybe we can go to the local scale, user specified scale, from 0 to 500 in value. We'll check. So see, 500 is very much high in value, 1 by second square. So these are the areas where huge eddies are being formed. So that is so much obvious from our velocity. Initially what we have found here, that velocity, the eddies are forming here, and this is least occupied areas by the benzene. So that is obvious. So here are the eddies forming in a greater extent. So maybe now we can go and try to plot by keeping some point, maybe at we'll just switch off and we'll try to create a point. So it is created somewhere here. I'll try to increase the value of y, which I need to increase to some extent. So I'll just try to keep the point here at the outlet and see how the pressure has been getting varied. Velocity. Right. X, I need to reduce the value. It's okay. So now we'll try to have that plot with respect to the variation in pressure, temperature, and all the stuff. Select the point. X-axis is time and y-axis is pressure. Click apply. With respect to time at that opening, how the variation of the pressure and velocities have been. It was taking time to note all the data points what we have mentioned. So yeah, 80% of it's completed. So now we also have try to plot the velocity also, how it is getting varied. So initially velocity at that instant it is 0, but once when the methane gas entered, so you can see the pressure values, how are they getting varied. Sudden jerk going there, and again it being constant. So this all due to the eddy formations, the pressure variation. So now you can also go to velocity, check for velocities. And if you can take the phase 2 fraction, and if you try to plot also instantaneously, there will be no phase 2. And as the time progresses, at some point the phase 2 will enter into the action. So this helps in you understanding how the pressure and how the velocity and how the any other phase of gas that has been occupied in the cabin getting distributed. So it would be helpful in your projects or any other knowing. So this is the velocity, how it is getting varied. Initially the velocity is on a sudden high and it is again getting stable. So now we will just check the phase fraction of benzene vapor as a final thing. So it was taking some time. So I think this video is helpful for you guys. As previously I used to say the same thing. Please do subscribe the channel and encourage me in doing more number of videos. If you have any queries in this particular video, please post in the comment section. I'll try to give the answers to the questions. So yeah, you can see on the screen how the phase 2 volume fraction. So initially it is 0 up to some point. It's around up to 0.025 seconds. It is 0, and suddenly it is getting raised. So it is so obvious. Okay, thank you guys.